Hello and welcome to this video in which we'll be looking at the second simplest neural network example. I've been requested to make a neural network example with a slightly more complicated network from the previous absolutely simplest neural network in my first video. So we will be looking at first a neural network with two input nodes, and after that a neural network with two output nodes. So let's begin. First of all, our weights are similar to what we had before. Of course, now we have two of them corresponding to the two inputs. So this is a fully connected layer here. And the output activation is the sum of the multiples of the inputs and weights. As before, we have a training set for the input 1.5 and -4. We would like the output to be 0.5, and currently, of course, it's not. Well, first of all, we need to define the cost function and get the derivative of the cost function. We'll use the same mean squared error cost function as in the previous video, and its derivative is exactly the same as before. The difference starts when we start looking at the rate of change of the output activation with respect to these two weights. There are two of them instead of just one. Otherwise, this is almost the same. And since there are two of them, I just want to mention that this is called a Jacobian matrix. Of course, this is a special case of a matrix because it only has one column, so it's not really a matrix properly speaking. You could rather call it the gradient vector. But you may stumble upon this terminology in the future. So a Jacobian matrix simply means the rate of change of a vector valued function with respect to vector input. Anyway, that's the gradient vector, and as before, these gradients are easy to define. They are simply the inputs. So if you take the derivative of this expression with respect to W1, this part goes to 0, and the coefficient in front of W1 becomes our derivative. So there we go, I1, and similarly I2 for W2. And again, using the chain rule, we can get the rate of change of the cost function with respect to W1 like this. So the rate of change of the cost function with respect to A times the rate of change of A with respect to W1, or in the case of the other weight, W2. So everything is pretty much like in the first video, so you can refer to that if this is confusing to you. Now let's look at the activation. In the first video, we had an activation that looked like this, a simple one variable first order polynomial, and its cost function, the cost function we used the same mean squared error also in 2 dimensions. Now, however, things are a little bit different. So the activation, first of all, is a plane in 3 dimensions, and here I'm illustrating that with colors. So with W1 increasing, the activation increases, and as W2 decreases, activation increases. If you remember, I2 was negative, so that's why these are the high values over here, and these are the lower values over here. So it's a plane increasing and decreasing in this direction. And our current weight values are here, 0.3 and 0.7, and our output activation is minus 2.35. So we want that to go up, right? Similarly, for the gradient, if we look at the values for the rate of change of the cost function with respect to W1 and W2, so here at each point we would put the values, the weight values in, and see what is the rate of change of the cost function with respect to W1 and find that it's that way, and for W2 and find that it's that way, and the resultant vector would be this one here. So these arrows show you the direction, not the magnitude of the change. So as you can see, spoiler alert, the area where the minima are going to be is here. Actually, there is an infinite number of minima. So actually getting ahead of ourselves a little bit, but that's all right. Any pair of weights along this line would be an acceptable answer to our optimization question. So here we have taken the input 1.5 minus 4 times by the weight, multiplied by the weight vector, and set that to 0.5, and this is the line that is plotted consequently. All right, so how do we optimize? Well, we optimize just like in the one-dimensional or the single node case. So each of these weights, W1 and W2, will be changed or adjusted based on the same formula as before: learning rate times the rate of change of the cost function with respect to that particular variable, W1 or W2. And let's actually look at what that looks like in spreadsheets. So here I have put all the variables in. So we have the desired output 0.5. We have a learning rate 0.03. I'll get back to that in a second. Then we have the input 1.5 minus 4, and the initial weights 0.3 and 0.7. And the current activation is simply the input 1 times the weight 1 plus the input 2 times the weight 2. So there we go, that's just as we saw before. And now we start adjusting. So the new weight is the previous weight minus learning rate times the input. If you remember, this was the derivative of the activation with respect to W1. It turned out to be the input coming into that connection, times 2, that was from the derivative of the cost function, which was a squared function. So the 2 goes in front, and we have the output, the actual current output, minus the desired output. And so our W1 goes up to 0.56 from the previous 0.3. Similarly, for the other weight, previous value of the weight minus learning rate times the input times 2, and the actual output at the moment minus the desired output. And this one ought to be marked as constant. So there we are. And so this one goes down really fast with this learning rate. So it goes from 0.7 all the way down to 0.016. And yeah, the activation starts looking like 0.5 very rapidly. Now you might wonder why the learning rate is so small. Previously we used 0.1 in video number 1, and this is the reason. Instead of converging, the network diverges if the learning rate is too high. So it goes from -2 activation to 8 to -20 to 54 to 104, -140 to 373 to almost 1,000 negative to over 2,000 positive, -7,000, and so on. It goes crazy. So we need a smaller learning rate, and some experimentation might be required to get to a good value, but this was the value that I ended up using. Could be a little bit higher maybe. But anyway, that is how we have optimized, and finally we get to this result that W1 ought to be something like 0.534 and W2 ought to be something like 0.075. And here I've spelled out the same if you want to go through this math on your own. Now visually what this looks like is we simply go closer and closer at each iteration to this line. So every time we input those values and get a new value for W1 and W2, we get closer and closer to this line, as one would expect. So the second neural network we're going to be looking at has 2 output nodes and 1 input node, same weights. But the activation, of course, in this case is a vector, and it's a little bit trickier to plot 2 weights to 2 activations, so I'm not going to attempt to do that. But everything else is the same, and we can treat the whole thing very similarly, except the cost function now looks a little bit different. Mean squared error actually starts having some meaning to the word mean. We take the average of these squared differences, and so we get the difference between the activation value at each point of the vector and the corresponding desired output activation. That's squared, and we take the average of those. So in our case of having only 2 values, it looks like this. And just as before, we have to get the derivative of that. So the rate of change of the cost function with respect to A1 and A2, those look simple enough. And finally, we can get the rate of change of the cost function with respect to W1 and W2. And their derivatives, of course, are just as before. They're I1, so that's right here. So this multiple rate of change of the activation with respect to W1 and W2 is I1, and you multiply by the rate of change of the cost function with respect to the component of the activation vector in question. And this first part here is simply A1, where I've substituted A1 with the input times the weight. And in this case, the cost function looks a little bit different when we look at the plot. So it's actually this bowl, if you will, in 3 dimensions, and this is far more interesting than our first order cost functions or 2D second order cost functions in the past. And this is how it looks in colors. And similarly, if we take the rate of change or the gradient of the cost function with respect to W1 and W2, we see that we've got these arrows that are pointing away from somewhere in this region here. So as you get farther and farther away, the cost function increases in value. That's what a gradient means, the rate of change. So let's optimize. And now this is interesting because it's exactly the same as what we had in video 1. You could take these 2 parts of the network and treat them as if they were a single neural network, the same kind as we had in the first video. And so we simply take the rate of change of the cost function with respect to the weight times the learning rate. So nothing complicated there at all. And again, let's use some spreadsheets to unravel these mysteries. So we have the desired output 0.5, 0.5, learning rate 0.3. You can see that it's a lot bigger, 10 times bigger than we used in the previous one. The input is 1.5, the initial weight 0.3 and 0.7. The activation is currently 0.45 and 1.05. And as before, we start adjusting the weights. So we take the current weight minus the learning rate times the input activation times the output minus the desired output. And we do that for weight 1 and weight 2 separately, and type in a bunch of iterations until we start getting to where we want to be. And we find that both W1 and W2 need to be close to 0.33333. And of course that on this plot would mean that we go from 0.3, 0.7, which is about here, down to about here, hereabouts. So that's where the minimum can be found. So that's it. Now we have optimized both networks and found the optimal weights. In this case, there is only one combination of W1 and W2 that is acceptable, that produces the correct answer. And in this case, there is an infinite number of combinations, but they have to be on that same plot or the same line. Again, if you have any questions or comments, please write below. And thanks for watching. Have a great day.